Okay, for our next concept is talking about the MLSS concentration and also the concept of SVI and their related correlation between the concentrated sludge in your acetylene tank and also the recycle ratio that is related to the concentration of your MLSS in the aeration tank. Okay, so here we can understand in that okay the MLSS concentration, as we call as a biomass concentration for the aeration tank, is the major design decisions for your activated sludge process. Okay, so it's how you maintain your MLS concentration in your systems is depends about many factors also like the settling characteristics about how much concentration you can get during your sludge concentrated uh, stage and also the rate of the recycling of the sludge from the settling tank back to the aeration tank. Okay, so we can have like the also from the balancing of our reactors here. So we know if we want to determine this is your reactors got your biomass concentration as your MLSS here, and you will have like the settling sludge concentration. So here the MLSS is concentrated, and here is your uh, recycle ratio of your float and flow back the biomass back to your systems. So, uh, okay, so during the moment, we know the relationship between the biomass in your reactors and also the returned sludge flow rate is uh, showing in the equation 11.6. So we know the here is your input, which means the Q in the influence times your X concentration. No, it's input as here. Here is your input will be equal to the boundary here is the output. So here is the output as a QE as the inference flow rate times your XE, the efferent biomass concentration, and plus the for the acetylene recycling flow here is the QS times your XS. Okay, so this is the mass balance in your acetylene tank. So during that moment, if we just assumed the QE times XE, which means the XE in the efferent biomass concentration is pretty low, okay? So we can just ignore these terms as 0 here. So we got the QI times X equals to the QS times XS, okay? And then we can also replace the QS as our QR, which means the flow rate for your recycle ratio here. So we know the QI equals to Q plus QR. Okay, here. Okay, So let's begin as like Qi equals to the Q plus your QR, like the Q0, okay, plus your QR. So here we can get like for our from the equation 11.6 here we got Qi of x equals to Qs times xs here, and because of the Qi equals to Q plus QR, so we got the Q plus QR times x equals to your QR times your xs. Okay, so we got the qx plus qr x equals to qr times xs. Okay, so we can just rearrange the equation. We got the qx equals to qr, the xs minus x. Okay, so we got the x equals to qr divided by q, the xs times your minus your x. Okay, and here okay, understanding that here is the qr divided by the q0. Okay, is the q0 is the recycle ratio, so we can replace this by the r. Okay, so we got x equals to r times xs minus x. Okay, so here we got the okay, here is the equals to r xs minus rx. So we can move these terms to the left hand side. So we got 1 plus r of x equals to r times xs. So x will get like 1 plus r, and here r times your xs here. So you have like the biomass concentration in your aeration tank will equals to, here is the correlation for the recycle ratio times your concentrated biomass in the settling tank. Okay, so that's why those two factors will affect your biomass concentration in your aeration tank. Okay. So we will see like here in the figure 11.5. Okay. So we can understand that there's like a different recycling ratio, and also here is the xm milligram per liter. So here is the recycling, which means the concentrated and recycle sludge concentration here. So by increasing the concentrated sludge concentration here, we can know if we just have a very uh, uh, low recycling ratios here, then we can have like a more activated sludge in your uh, aeration tank. Okay, and this, if we want to determine like uh, the recycling sludge concentration here, sometimes we will apply like the SVI to determine, okay, the settling sludge volume test that we call here to determine the concentration of XMR. So by using the SVI here, the SVI is based on the definition of uh, during a period of time such as like the V30 like for the 30 minutes. Okay, if we put the activate sludge into like uh, uh, settling cylinders for 30 minutes, and then we will note the total volume of the cylinders and the volume of the settled sludge after 30 minutes will be measured as our SVI. Okay, so when the SVI, typically good SVI is about 100 milliliter per gram. Okay, so which means they have a better settling capacity during for 60 minutes uh, period of settling time. Okay, so which means sometimes if you got a good SVI about 100 milligram, 100 milliliter per gram, your XM range for the recycle concentration will be around about 10,000. And during the moment, if you got like the SVI about 50 or less, that will means you will probably get your recycling sludge concentration about 20,000 milligram per liter or more. Okay, so SVI is kind of the index for you to approximately predict your uh, recycling sludge concentration. And let's move to the data section 11.5. See here. Let's talk about the bulky and the other sludge settling problems that will sometimes in your activated sludge system. So, as we just know that, okay, the sludge flux settling is if they are compact wells, there will be got very concentrated sludge in your settling tank. And so if those biomass that cannot be well settled in your settling tank, sometimes they will cause like unsatisfactory effluent quality, like you will have like a higher biomass concentrations in your effluent, and those biomass will contribute to like a BOD or COD concentration and to your inference qualities. Okay, so it's also got like make the SRT controls more difficult. Okay, so the settling of the sludge is the big issues to your activated sludge system. Okay, and we sometimes will facing few problems about the sludge that cannot be well uh, settled and concentrated in your settling tank. Here we list some like from the 11.5.1, the bucket sludge here, and then we also have this table to show most of the issues we were facing about the biomass separation problems. Like we just said, the bucking, and the bucking also including like the viscous bucking, relative, not relative to the filamentous organics. Okay, and also we sometimes will get like the thin flux, the pinpoint flux, and also the foaming issue. Okay, sometimes also the rising sludge. So we are seeing those few those problems that will causing you got a very bad sludge separations from your systems. So we turn back to the section 11.5.1. The bulking sludge is the most pervasive. Okay, the most pervasive problems that will causing with the activated sludge. Okay, so which means the activated sludge flux that settles slower, much slower, and sometimes their structures getting not so compact. So which means they got like a more loose structures of their flock and the aggregates, and making it almost quite difficult to uh, remove by the settling system. Okay. So if if we want to get like uh, maintaining the biomass in the aeration tank, and just when we are facing with the bulking sludge, sometimes we have to increase the recycling rate to getting more higher and higher recycling rate, because the concentration of the settled sludge is getting decreased, and also uh, those settled sludges uh, blankets will be rise until it fills the settler. So you will get like the sometimes you will get like the liquid and the solid the interface getting higher and higher. So you can't have the like very good uh, liquid and the solid separations in your system, and those floating sludge will eventually flow out to your system. So that's why you cannot control your SRTs here. Okay, so as we just mentioned that we just think about the scorial microorganisms that is contributes to the EPS releasing to have the like the glue to attach all the bacterial cells together to get the aggregate and the flock as the activated sludge. Okay, but if you are facing with those bacteria that will have like extended filaments that will creating those like bridges between flocks, so they will have like extend the space between the flocks and also the cells, so they will have like cause very negative effect. Okay, so the extended filaments they will cause in the bridges, and then the bridges will prevent the flocks to coming closer together, and so sometimes they will get a very bad effect to their compacting. Okay, so as we just mentioned, the how do we determine the uh, settling capacities? Sometimes we use SVI. So for understanding the if your activated sludge is getting bucking, you sometimes we will use microscope examination. The observation is very useful to you to uh, directly observe if there is any like bacteria that is forming the extended filaments things within the sludge flock. Okay, and the second thing is you can also measure the SVI. So if you got SVI greater than about 200 milliliter per gram, so sometimes that means you got the you will get a serious bucket after all. Okay, so especially when the SVI is getting higher to like 500 more per gram, which means you already got a very serious bucket sludges in your systems. So we generally will use a microscope examination as our best decisions detection tool to directly observe if there is any, like we just say, extended filaments in filament in your active sludge flock. Okay, and so there's few reasons will cause sometimes will cause the bucking sludge here. We just mentioned is like the low DO concentration and the high effluent ratio, and also you have like some reduced suffers that will as in your influent. Okay, so those few operations will sometimes cause you get the bucking sludge. Okay, that is because of the competition of the microbial communities. So talking about the low DO bucking is getting because of the fragmentous bacteria we call the Spherotilus natalis. And this type of the filamentous bacteria, they are very sensitive to the DO concentrations. So, which means they especially got very good affinity to the DO concentration, which means they got low K volumes for auctions. Okay, so if you have like you don't have enough oxygens supplied to your systems, you will get a like low DO concentration in your systems, and those filamentous bacteria will become predominant because they have low substrate affinity to the oxygens. They compete the oxygen, the dissolved oxygens much more easily better than the other heterotrophic bacteria. Okay. Okay, so this is one reason that we're causing the bucking sludge. And the other type is called the low FM ratio bucking. Okay, so here is low FM ratio. Okay, so especially when you have to maintain your system in a very low HRT, some still fragmentous bacteria will also become predominant in your system, especially under a very low effluent ratio. Okay, so for example, the Mycothrix and also the genus of Helicobacter. So those two filamentous bacteria will sometimes get in a higher predominate in your system, especially when you got very low effluent ratio. So those bacteria are called, we call the cat strategies bacteria, and compared to the other are called the R strategies bacteria. Okay, so case strategies. If we got the substrates, this is the mono equation plot. We got the mu here, and we got the substrates here. So for the case strategies, bacteria, sometimes we will have those correlation between the substrate concentration and also the growth rate, just like this. Okay, so this is the case strategies. And compared to the other, will be like the R strategies is something like that. That is the R strategist. So which means when you are handling like low substrate concentrations here, those bacteria that belong to the case strategies microorganisms will have much better, or we call it a higher growth rate compared to the R strategies microorganisms. So those filamentous bacteria that we just mentioned, microthrix, and also the Helicobacter, they are all belonging to the case strategies bacteria. So under the low FM ratio conditions, they will generally get like predominant in your systems and causing the bucking sludge. Okay, so sometimes they will exist like our previous mentioned the extended aeration tank. Okay, so those are uh, very bad for your systems if you have to like settling down those activated sludges. Okay, so how to prevent those two like a low DO? It's quite of the easy way to prevent in the low DO buckings. It's just providing good oxygens, dissolved oxygens concentrations in your systems, and to about preventing the low FM buckings. Sometimes we will use the select tank, the strategy of using select tank, and it's placed in front of the aeration tank, so it will receive the influence, and also those sludges recycling from the settling tank will receive the highest amount. Here you got the high organic concentration, and so those recycled sludge will get contact with those high organic concentration influence, and in this case they won't, and they can like update those biodegradable organics very fast, and then get competed against the uh, we call the case strategies filamentous bacteria. So this is the strategies we will use and to prevent the low FM ratio bucking here. And also additional, sometimes we will have the reduced sulfur bucking occurs. So those are associated with the sulfur oxidizing species. Those filaments bacteria, they are using like the sulfur as their electron donors, so such as the Theothrix genus, and so they will gain competitive advantage from the chemolithotrophic electron donor. So if you got those donors, they will get in your influence. So you will have like the chance to promote those sulfur oxidizing uh, filament species to get growth in your systems. Okay, so in order to prevent this, like reduced sulfur getting into your system, so sometimes we will use like hydrogen peroxide to doing the oxidations in advance to the aeration tank. Okay, so those three are very general problems that will cause in the bucking sludge in your system. Okay, so about the 11.5.2, we are talking about the foaming. It is another issues that will cause your sludge unsettled because they have like lots of the bubble exists in your system because of the foaming. So the foaming, which means sometimes they'll generate lots of the maybe like the proteins, the polysaccharides, those kind of the substrates, and those substance will causing like uh, they have like the just like a detergent, and those detergents will causing bubbles when you are doing the aeration. So those aeration, after the aeration, those bubbles will flow up to the top of the reactors and causing your sludge will be attached to those bubbles. So under these conditions, you won't get very good settling uh, capacities in your settling tank. So about those bacteria that were causing the foaming problems, sometimes they are belongs to the general nocardia and also the mycothrics, and those bacteria are belonging to like slow growing bacteria. Okay, so sometimes they are associated with like a long SRT operation, and sometimes with high wastewater temperatures will have the chances to make the nocardia and the microflux bacteria getting more and more in your systems, and they will producing those as we just say the like the protein, the detergent, the surfactant, those chemicals out of the cells and causing the foaming problems. Okay, and about the rising sludge here, we mentioned in section 0.5.3 that is coming from like the gas releasing from the sludge metabolisms. So which means like the if we are having more uh, like the nitrification, we will just introduce later in the nitrogen biological nitrogen removal systems. The denitrification is a process that will convert to the nitrate to the nitrogen gases. Okay, so when you have those kind of the sludge that exists in your systems, those releasing gases will changes your like activity sludge to getting flowed up to the top of the reactors. So they will accumulate those metabolite and metabolisms of gases in your sludge blanket. So you will get your sludge getting lighter and to getting upper to your systems. So those gas bubbles will attach to the settling sludge particles and floating up to the top of the settler. Okay, so not only the sludge of the uh, denitrification process, but also the sludge for the anaerobic systems about the methanogenesis will generate like the methanes as their biogases. Okay, so this kind of the problem is called the rising sludge. So that's basically caused by the gassing bubbles that flow up to the system. So The most effective cure for rising sludge is if you don't necessarily need those kind of the nitrogen removal process, you can remove them to uh, away from your activate, activated sludge process. So like if you don't need a nitrification, you don't have to get much longer like SRT to convert all the ammonia to the nitrate, and you don't even need the denitrification process. Okay, so you won't get like nitrogen gases in your system. Okay, after our discussions about the aerobic suspended uh, systems, we're going to talking about the membrane bioreactors. And the membrane bioreactors actually is the advanced version of the activated sludge systems. So uh, the membrane has a different type of the label and depending on their pore size. So if we are going to understanding the membrane separation principles is actually uh, doing the separation of the liquid and the solid. Okay, so it's kind of using the driving force across a selective permeable membrane. So you will be able to separate the solid from one side and also let the liquid passing through the membrane pore. Okay, and we have they are using the principles of the size sieving. So that's the mechanical filtration process using like porous membranes. So we got different levels of the membranes, including the microfiltration, ultrafiltration, nanofiltration, and also the reverse osmosis. So those levels, depending on their pore size, as we can see in the figure 30.1 here. Okay, so about the conventional filtrations is using like the same filtration or the other type of the granular uh, filtrations. They are focusing on the level about 10 to 100 micrometer size of the particle. But if you are using like the membranes, they are going down to the level of the below 1 to 0.1 micrometer. This is for microfiltration. And when you are going down to the ultrafiltration, your pore size level is getting down to the 0.01 micrometer. And you can also given to more small uh, size of the pore particle, pore size, including your nanofiltration and the reverse osmosis. So that's basically is belong to 0.001 micrometer. So under these levels, if we are considering by using the membrane, including them to the activated sludge systems, so most of the membrane is membrane modules. Their purpose use of the membrane module is going to replace the sedimentation tank or the secondary clarification tank, as we just talking about previously. So when you are going to separate the solid particles of activated sludge, so sludge size is about like 10 to 100 micrometer size. Or if you are going to separate even a single cells, so like the E. coli cells, they are ranging about 0.5 to 1.5 micrometers. So by using the microfiltration and the ultrafiltration membrane, they are able to uh, separate the active sludge very well from your effluent. So that's the development of the membrane bioreactors. So basically, if you are going to uh, using the membrane bioreactors, so most of the times we're using the MF and the UF membranes, they will get you the more like permeate flux, and also you will have like the better separation uh, efficiency. And let's move to the next page here. The 13.2.2 sections, we're going to talk about the membrane bioreactors features. So, which including the advantages of the membrane bioreactors compared to some traditional like activated sludge system. Okay, so we already know that the MBR is the combination of the biological process and also the membrane process. So the biological process is talking about like the activated sludge process. Okay, so if we are imagining that there is activated sludge systems, you have like the aerobic CSTR, okay, and including like a secondary clarification tank, and have like the recycle for those sludge systems. Okay, so which means you have two reactors and also lots of the pipes. Okay, so the MBRs by replacing the secondary clarification tank by using the membrane process is going to reduce the footprint of your whole systems, especially when you are using like the immerse uh, membrane bioreactor. So let's discuss about these two systems here. Okay, so for the upper one, here is your bioreactors. Okay, so which means your sludge is staying here, and when you are going to flow out your effluent from your bioreactors, those effluent will directly go through a membrane modules here. Okay, so if the membrane module is outside of the bioreactors, we call it as a side stream MBR, as a SMBR. So the sludge will be accumulated here. Okay, and then those effluent will come out passing through your membrane, and those concentrated sludge will be flow back to your systems. So this is for the sludge returning. Okay, so this is kind of the just put the membrane modules as a replacement of the secondary clarification tank. However, if you are using a different type of the MBRs, which means you put the membrane modules directly inside your bioreactors, we call submerged or immersed MBR. Okay, by using this kind of MBR, you don't have to provide additional tank or additional places to put the membrane module. You just put in your original bioreactors, and your effluent is still passing through out. So that's your effluent. And however, the concentration of the membrane of the sludge is directly happened in your bioreactors. So here the sludge will be separated directly into your bioreactors. And if you want to test any kind of the waste sludges, you can directly take out from your bioreactor. Okay. So by using the submerged MBR, you will have you will have the advantage of the reduced footprint for your whole system because you don't have to provide additional places to put the member module. Okay, so that's the first advantages. And so that means you will have like a very high biomass concentrations in your bioreactor because you continuously concentrate or accumulate those sludges in your bioreactors. And by doing this, you got high MLSS concentration. So those, if they are active microorganisms, and then you will be able to degrade more BOD, COD from your influent. So the water quality will be increased in terms of the COD and the BOD removal efficiency. And also because you remove all the VSSs from your effluent, so your water quality about the VSS in the effluent will also be reduced. Okay, water quality will be increased. Okay, so that's basically because the membrane rejections. Okay, for those VSS particles. And the most important advantage of the development of MBR is because of the you can easily control your solid retention time, the SRT, and the hydraulic retention time independently. Okay, so that is because by understanding the flow stream here, so first of all, your liquid flow stream is coming here and then they passing by your bioreactors and passing through your membrane modules. So here is your HRT. So just depending on the flow rate of your effluent and your effluent. And also here is your Q inside your bioreactors and also using the pump to get out of the effluent. So here you can control your HRT. And because of there's no naturally sedimentation process in the MBR, so your sludge waste streams will just come out from your bioreactor. Okay, so because all the sludge they are not coming out here, there's no sludge in your effluent. So you can just easily control how much amount of the sludge you are going to toast from your bioreactors. And don't have to worry about any kind of the accidental washout from your systems. So that's basically a better systems because you can easily separate the solid and the liquid out of your system. Okay. So in that moment, you will have very high MLSS concentrations in your system. Okay. And also because you can control the SRT, independently to the HRT, so you can also reduce the sludge productions because you keep more biomass in your bioreactor. Okay, so this basically for advantage of replacing uh, the secondary clarification tank by membrane modules. Okay, and let's move to the next page here. Okay, so the development of the membrane MBR. Okay, there's becoming different development for different purpose. So for like they are going to have like a new membrane configurations, okay, including by using like making the suspended solid become granular sludge, okay, or we can hybridize with the biofilmed MBR. So this is kind of the advantage of the new kind of the MBR configurations, because you not just let the membranes directly connect to the sludge flock. That's our typical form of our activated sludge. However, you are changing the activated sludge flux into like a granular sludge or the biofilms attachment sludge. Okay, and also you will have like the purpose for wastewater reuse that you can combine more. So the MBI here we know is like the MF and the UF. So you just separate solid and the liquid. But if you are going to reuse those liquid, some of the like ions or even though more small like large molecular, okay, high molecular those chemicals you would like to remove, so you can going down to using combination with the RO systems to remove ions and also some high molecular chemicals. So for those MBR plus RO is going to use it for like wastewater reuse, and also you will get the MBRs for the very special microbial based MBR. So this is typically using for like the slow grower. Okay, for those slow grower, you need more time for their staining, so you will get a very high SRT here. So as we just mentioned previously, sometimes high SRT is going to keep your sludge become bucking. Okay, so that is why in the traditional activated sludge systems you are unable to perform those kind of the SRT conditions. However, if you are going to if you are using the MBRs, there is no uh, other like interference to your SRT control. So that's why you can just keep as long as you want for maintaining those slow growers to become predominant in your system. So here we can have like an example about the Anamox MBR. So the Anamox represent, we were talking about these bacteria in later in our nitrogen biological treatment system. Okay, so the MV Anamox. Okay, so is like the an aerobic. Okay, ammonia. Okay, oxidation bacteria. Okay, so they are doing by using the ammonia and the nitride as their electron donor in the electron receptors, then they convert to directly to nitrogen gas and plus a little bit of the nitrate. Okay, so you can just they can become the biogas, and by using the very easily one-way reactions to complete the nitrification and the denitrification. Okay, so the kind of novel uh, shortcut to your nitrogen treatment. Okay, but the Anamox uh, bacteria, they got a very slow growing characteristics because their doubling time is about 7 to 21 days. That is the in the under the nature conditions. But if you are using like the more high efficient like SBR system to grow those bacteria, they can shorten their doubling time to like 3 to 5 days. But it's still longer than the heterotrophic uh, bacteria. So that's why we have to use in like a membrane modules to keep those slow growers staying in the bioreactor.